Alright, so having discussed the industrial example, let's move on to an example associated with health, in particular disease transmission. So this is a video from Professor Lydia Gruiba of MIT, and for some years now she has been studying the fluid mechanics of coughing and sneezing, in particular in light of the transmission of diseases through respiratory droplets that are ejected when a person sneezes. A key aspect of this problem is to understand how far the droplets that are ejected during a sneeze or a cough manage to travel before they settle down. Now, especially in light of or during the time of the COVID-19 epidemic, there's been a lot of discussion about the minimum distance required for social distancing, and typically a value of about 1 to 2 meters, 6 feet has been going around. This is based on very old work in the early 1900s, and actually much more recent studies led by Professor Gruiba have shown that the spray that is ejected from a person's mouth can travel up to 10 meters, 8 to 10 meters distances, showing that the estimate of just 1 meter is way too small. So this is a movie that from her work that I will play now. Yes, so this is starting with a close-up near the mouth. So you see that as the person sneezes, this is of course a highly slowed down movie, you can see the droplets being ejected. Several of the droplets just move in straight lines, almost ballistically. These are the relatively large drops, but there are also a whole bunch of smaller drops that are carried along with the warm air puff that is ejected in the sneeze. The basic picture that develops from here is that you have some droplets that just fall ballistically or move like as if it's not affected by the flow. But there is also a huge plume of warm air that is strongly turbulent, that entrains all the smaller drops and causes them to hang in the air for a long time. It is this turbulent plume or puff and that suspends the droplets and allows them to stay in the air much longer than expected. Here you see that this turbulent puff can easily travel up to 8 meters in distance while remaining in the air. And all of this has to do with the mechanics of turbulence and entrainment of jets. Something I want you to notice here in this last video. Yes, you see the initial puff moves downwards, but then it starts to go back up again. This is because of the buoyancy of the puff, the fact that the air that comes out from our mouth is warmer than the environment, than the room temperature typically, and therefore it tends to rise. So this is an exciting area of work in general, and clearly shows the importance of understanding, in this case, two-phase fluid mechanics turbulence, along with the transport of temperature in the puff, as well as the droplets and the viruses inside the droplets, and so on. So although this problem is beyond the scope of our current course, because the flow is turbulent and multi-phase, nevertheless many of the basic techniques we will be using in the course, scaling, asymptotic methods, and a basic way of analyzing a transport problem will carry over to even more complex problems. And so this course can form a foundation for more advanced courses that you might take in graduate school. Alright, and this leaves us now with the third example I have for you, which has to do with the climate. This is an image from NASA, a video rather, which shows the concentration of carbon dioxide as imaged from a satellite. Let me just play it for you. And you can see the progress of how the concentration of carbon dioxide changes with the seasons, as you see the date shown here below. The carbon dioxide concentration is high wherever you see red, is low wherever you see blue. and the difference in the northern and southern hemispheres has to do with the fact that one hemisphere sees summer, the other sees winter, and therefore has a different amount of tree and foliage coverage, vegetation that is, that absorbs carbon dioxide through photosynthesis. You can see clearly how the distribution of carbon dioxide is strongly modulated by the presence of winds and atmospheric circulations. So that even though carbon dioxide really is released, let's say, through heavily industrialized areas, you see in industrialized parts of in most of the US, industrialized parts of Asia, and so on. Nevertheless, what is released in one area is transported to other areas of the world, and indeed the entire Earth is interconnected through the global circulation. And so understanding not only the transport of carbon dioxide but other pollutants in the atmosphere, dust, aerosols, and so on, requires an intimate understanding of the fluid mechanics of our atmosphere and the oceans as well, because the atmosphere interacts with the ocean through mass transport, through evaporation, rain, and so on. You see now, as we approach the middle of the year, that the southern hemisphere starts to pick up in its carbon dioxide concentration, and the picture inverts, while the northern hemisphere clears up. Yes. And throughout you can see the dominant role played by ocean currents, atmospheric currents. Alright, so let's move on. This also, by the way, shows you the beauty of flows in general across a whole range of scales. Okay, now that we've looked at some examples in nature and industry, I want to show you a couple of examples that highlight sort of the beauty of the subject and the fact that you can encounter principles of transport phenomena in your daily lives in the simplest of situations. So what we have here is basically a layer of liquid at the bottom of a washing machine, and what's going on is that the clothes in this washing machine, this is a top loader, so the washed clothes have been transferred into the neighboring dryer, and the dryer has the neighboring spin cycle or the centrifugal, and that has been switched on. So as a result of the spinning drum spinning away, the entire washing machine can shake, particularly if you have it lying on a not even surface or a slightly older washing machine. Then the vibration of this washing machine is what is causing the liquid layer at the bottom of the empty drum to vibrate. And the key point is that as the liquid vibrates, it generates these intriguing hexagonal patterns that you can notice right here. You see the presence of hexagons, almost crystal-like, in the vibrations of the liquid. Now these fascinating patterns arise from an instability seen most clearly by vibrating a liquid layer from below. So this is a video of, and what these are called are Faraday waves. So essentially you have a petri dish with some liquid on top of a vibrator, and you will see that as the vibration amplitude increases beyond a certain threshold, the fluid surface spontaneously develops patterns which turn out to be hexagonal and look exactly like what we saw in our washing machine. So this is a problem of stability because the flat interface can vibrate vertically in response to the vibration of the bottom wall and while remaining flat. So that is a possible solution, but it turns out that that is unstable, and instead what you get is a deflected, deformed free surface that takes the form of these hexagons. This was first noticed by Faraday in the context of a granular flow, and hence they've been called Faraday waves and have been extensively studied, and we will look at such stability problems towards the end of our course. Here's an example of Faraday patterns in nature. So what's happening here is the alligator is vibrating its back beneath the water, and that causes the water surface to develop Faraday waves so strong in fact that they eject droplets. The purpose of the alligator vibrating its back is to generate a sound that attracts mates, and a side effect of this is the Faraday patterns it produces on the water surface. Alright, here's another interesting situation where the beauty of flows are apparent. This is the case of lava freshly rising from the earth and flowing along a gently sloped surface. You see it because of a combination of rapid cooling at its surface while the lava below the surface remains hot. This leads to buckling and folding instabilities, as you can see here in these images. Also, if lava falls in the form of a waterfall, it tends to undergo this folding instability at the bottom. Which are rather beautiful. These flows are entirely laminar, but strongly modulated by the fact that the viscosity of the lava is a strong function of the temperature. And this is an example where the transport of heat is strongly coupled to the flow itself. These ropey folded patterns are called pahoho, which means to paddle in Hawaiian, and these are all pictures in Hawaii. So one problem which we will try to address towards the end of the course related to this lava problem is that of lava chimneys. So one common way in which lava rises to the surface, apart from of course big volcanoes, is through narrow fissures in the Earth's crust. So what I want you to imagine that there is a small crack in the Earth's at the surface of the crust that runs deep down into the magma below. What can happen is this crack that is formed through various geological processes can allow for the magma to rise up as a sheet. And the image on the right top shows such a sheet of magma. But what is observed is that after the eruption of this sheet, which is called a fire curtain, with time over several hours, this fire curtain tends to evolve from a continuous sheet into a series of spouts or chimneys. And what's remarkable here in this image, and quite general, is that these chimneys have a well-defined separation between them. Such a spontaneous channelization, let's say, with well-defined spacing is really a pattern, a spontaneous pattern. And this is a hallmark of a fluid dynamic instability. That is the natural self-organization of a pattern. So one can ask, what is the mechanism? So typically when we try to address such problems, the first step would be to consider the problem in its simplest setting, which is something that we will do time again in this course. In this case, imagine that you have a flow of a liquid between two parallel walls with a thin gap between the walls. This is to mimic the small crack or fissure through which the magma has to rise. The fluid itself that is supposed to represent the magma, in the simplest case, would be taken as a Newtonian fluid, but whose viscosity depends on the temperature of the fluid. So we are incorporating only one aspect of a magma fluid, which is a really complex fluid which has bubbles and crystallization and many things going on. But one aspect which is very clear in such a fluid is that as it cools, it tends to become more viscous because of internal solidification and so on. So we will account for this aspect. What we will also have is that at the bottom of this channel, the fluid is hot at a temperature Th, whereas the walls of the channel are kept at a colder temperature Tc. This is to mimic the cold walls of the fissure in the crust. So what happens naturally is as the fluid rises up as a sheet, it tends to lose heat to the cold walls. Therefore, as the fluid rises, it cools and its viscosity increases. So you have hot fluid cooling and becoming more viscous as it rises. What one can show is that just with this simple model, there is a chance of an instability forming, which spontaneously leads to channelization. So this is a picture showing exactly that. You see a simulation where the color shows you the temperature. You have hot temperature at the bottom and cool temperature at the top, and the lines show you the streamlines of the flow. So initially we have a uniform flow, everything is moving vertically up, but if you give a small disturbance under right conditions, you can ask whether it returns to its uniform state. So in this case, the theory predicts that the flow should be stable and it should remain uniform, and that's what we see. But under a different condition, a different kind of disturbance, you see that the initial disturbance starts to grow and all the fluid starts to channelize into small channels. Essentially what is happening here is the fluid spontaneously tends to form channels, so most of the fluid is flowing now through the edges of the domain. As a consequence, there's a very slow fluid through the center. Because of this, the fluid that is flowing slowly loses heat faster, becomes more viscous and flows even slower. On the other hand, the fluid flowing through the sides flows faster, it therefore has less time to lose heat, therefore it remains hotter, therefore it's less viscous, and this allows it to flow even faster. This is the kind of nonlinear feedback that gives rise to the instability, and that's why the initial disturbance that you see keeps growing. And so the fluid that flows a little faster remains hotter, stays less viscous, and can flow even faster, and so on. The reason this does not happen in the first case is because this effect is counteracted by viscous forces and thermal conduction, which try to uniformize the temperature and the flow. Alright, so we leave the example there and turn to it later, hopefully during the course. Now what I hope these examples have shown you is that there is a wide variety of problems in industry, in nature, in healthcare and so on, where understanding of fluid mechanics along with heat and mass transport is essential. This course will equip you with all the techniques and conceptual approaches that you need to analyze such transport problems, in particular to write down the governing equations with appropriate boundary conditions, and then to analyze them systematically using the methods of scaling, approximate solution techniques, and when called for, certain numerical simulations. So with that, let me take you through a brief outline of the course and the plan of lectures. So we will start with a few lectures on the basic principles. That is, we will begin with a discussion of certain subtleties of the continuum approximation or continuum approach. We will then derive the form that the conservation principles of classical physics takes within the continuum approach, that is the partial differential equations expressing conservation of mass, the equations of mechanics, and conservation of a single scalar, as well as heat or temperature. Once we have the basic equations down, we will then start taking simple problems that allow us to introduce the methods firstly of scaling and non-dimensionalization, and then of perturbation and approximation methods. These are closely related. Scaling allows us to identify systematically the terms and their corresponding physical effects, which are small relative to other effects in an equation. This is typically done through identifying non-dimensional parameters which are small. This then forms a basis to develop approximation schemes based on the smallness of these parameters. These are called perturbation methods. Once we have these basic techniques down, we will then take on more intricate examples and work them through from start to finish. Each of these examples will illustrate the combined application of these different methods, and all of them will call for a continuous interplay between the mathematical methods and the physics of the problem. And towards the end, we will look at examples that look at coupled heat and mass transport, and finally we will also consider some cases of hydrodynamic stability and the spontaneous formation of patterns that arise from such instabilities. One reason to do this, of course, as I already mentioned, is that the approximate solutions that we derive, while being approximations to some valid solution, need not be stable. And that is why often in a numerical simulation or in a laboratory, what you see may be a more complex flow, and not the simple solution that we derive. Nevertheless, even those complex flows can be understood often as instabilities of the simpler flow, and that's where instability analysis steps in. Another reason to do this, and a more enjoyable reason, is for the sheer beauty of the patterns that arise, and the beauty also of the analysis and the questions and intricate mechanisms associated with these spontaneous patterns. Now, one of the primary resources we will be using is the book Advanced Transport Phenomena by Gary Leal, a Cambridge publication 2007. If you can get yourself an electronic or physical copy of the book, it would be great. And you could start by reading his first chapter, which covers his preface, and his first chapter, which covers various aspects of things I have discussed today, including the general philosophy of the subject and reasons to study the subject, the importance of asymptotic analytical approaches, and so on. His second chapter also gives a very nice exposition of the basic principles. We will be following parts of that chapter in our development, but also supplement it with some more advanced material from other books, which I will introduce as we go along. Most of the example problems we will do are also from Gary Leal's book, but then again we will also take some from modern research papers. And so with that, I welcome you to the course. I hope you are excited to study more about advanced transport, to learn about scaling and perturbation methods, and to begin analyzing these beautiful and intricate flows. So I will see you next time with the basic principles and the continuum model. Thank you.